So just a heads up that, of course, this is a college and the high school class. Usually it's around this time that people start saying, we still haven't registered for that college credit. Shouldn't we have done that a while ago? No, because it actually goes with the second semester's grade. So registration will actually take place in February. So those of you worrying about the college and the high school credit, that is still to come. That is still on the radar. It's just kind of looking ahead and the timing of it. All right, so for today, we are actually learning some new derivative rules. Well, a new derivative rule, because we're going to be learning how to find the derivative of this. We're going to find the derivative of f of x equals 2 to the power of x, and other numbers to the power of x. And the first thing we have to do is we have to deal with what it's not. Because this is not going to equal, or at least the derivative is not going to equal 2 to the power of x. That does work with e to the power of x, where it is its own derivative. But anything other than e to the power of x, it's not its own derivative. So in order to know what to do, first thing we should do is add into our notes the formal answer, the formal notes on what this is. So into your derivative rules page, please add how we find the derivative of an exponential. All right, so as you're getting this down, you'll notice that here we're doing the derivative of a to the x. So this is any number to the power of x here, basically is what it's talking about, because a's are constant in this case. And so you'll notice that it does equal a to the x. That's part of it, where the same a to the x is still there. It's just that when we find that derivative, we also have that same thing that we started with times the natural log of our base. So we can now do it, but we have to remember that it's got this natural log still hiding it. And so if we want to find the derivative then of this one that we first started with, f prime of x here is, yes, going to have 2 to the power of x in it, but what am I going to multiply the 2 to the power of x by? Yep. It'd be times the natural log of 2. So it's 2 to the x ln 2. All right, now of course we've seen stuff like this before. It was always e to the x. I don't want you thinking this is a new and separate rule. I want you to see how we actually still have been using this. We've just been using a particular instance of it. So use the rule that we just wrote down to find the derivative of e to the x here. We want to prove that it still equals the same thing. So if I use that new rule here, the derivative would be the same original exponential times the natural log of our base. But of course, we have not included the natural log of e in our derivatives before when we've done this, because what does the natural log of e equal? 1. And so that's why it's just e to the x, and why e to the power of x is unique, and why it is its own derivative. It just happened to work out to where, because that equals 1, that it is its own derivative. So that's why that worked out before. But yes, it's still using the same rule. That same old rule still applies. All right. Now that we have those figured out, we now can find derivatives of something that's a little bit more complicated, like these. So go ahead and find the derivative of each of these two functions, please. All right, so for this first one here, to find the derivative, I am going to be using the new rule we just took down today, but what other rule do I need for this? Yes, the chain rule. Because I have a function within the function. Specifically, this 3x plus 5 is my inner function here. That's taking the role of where I'd normally just have an x, and now it's something more complicated. So that's my inner function. So I'm going to start by doing the derivative of my outer function. So that's going to be 4 to the power of something times the natural log of 4. But then I have to multiply that whole thing, and I'm just going to throw in an extra set of parentheses to show that clearly here. Then I'm multiplying that whole thing then by the derivative of the inner function. That is the derivative of my exponent in this case. And the derivative of 3x, of course, is just 3. derivative of 5 is 1, or 0 rather, and so that goes away. So this is actually my derivative, which yes, we could clean up a little bit. And so I would go ahead and just call it as f prime of x equals 3 times 4 to the 3x plus 5 ln of 4. All right, and so that one's done. All right, and then for the next problem, when we go to find our derivative here, again, we're going to have to use chain rule because we got the sine of x where there's normally just an x. So we first do the derivative of the outer function, which is 5 to the power of the same thing, times the natural log of 5. Then I'm going to multiply that by the derivative of my inner function, that is the derivative of sine. The derivative of sine is cosine, and so that's my derivative. 5 to the power of sine x times natural log of 5 times cosine of x. All right, so we're kind of multitasking in a way today. We're actually getting a couple topics done. This exponential derivative is actually a fairly small topic, as you can see here. You probably already got it down really well. So we're going to be looking at one other thing today, which is a broader topic, and the start of a broader topic that we're going to be looking at here. We're going to be looking at implicit graphs. Implicit equations and their graphs to get a feel for what these things look like and how they behave, because we're going to be working with implicit equations here in the near future. Implicit equations, when we talk about that term-wise here, implicit equations are written in terms of both x and y, as opposed to explicit equations, which are always going to be like a y equals. So for instance, implicit equation that you have seen before in the past, a fairly common one would be like x squared plus y squared equals some number, let's say 25. That's an implicit equation because the x and the y are both kind of on the same side of the equation. It's not solved for one of the variables. That's going to be the case with these implicits. And so I'm going to be passing out to you a worksheet here in a moment. And on this worksheet, you're given an equation and then a graphing grid. I want you to basically go and make the graph. I would suggest that you use Desmos's graphing calculator for this. That's why we got the computers here today. And then you're going to then draw the graph on your own paper. And you're going to do that for each of the equations that we have there. I've given you a bunch of extra room because we will be making use of some more things with these in the next few days. But today it's just about the graphs and seeing how these graphs behave because they're a little bit different. In fact, they're very different from what you probably have seen before. And then once you're done making those graphs, there is a homework worksheet for tonight. It's fairly short. It's just a couple problems. The derivatives for worksheet. So when you're done with the implicit graphs, you'll come up and you'll grab one of those.